All right. Hi, everybody. So, last time we finished our section on financial math, which is exciting for me, and I don't know if that's exciting for you, but I must say I find it. I know it's super applicable to everybody's lives, and this is why I'm giving you this project to work on your own personal finances. Because I think it's really good for us, considering this is the world we live in, full of finances and complicated equations that determine how much money you have in the end. I mean, these are good things to learn about, but I must say they're not I don't find them the most enjoyable uh, parts of math. So today I'm going to talk about a couple of things that I do find really enjoyable, and hopefully you will too. And not only are they enjoyable, but I think they're applicable as well. Um, Today we're going to talk about some probability, odds, and expectations. So today, probabilities, odds, and expectations. Um, this is the entire of chapter 16 that we're not going to do all of today, of course, but this is the only day I'm going to talk about them. Because I think that a lot of these concepts are relatively basic. I think that a lot of us have kind of a natural intuition for probabilities. That we can use that natural intuition without defining every little bit of the maths that go into probabilities, which of course can get very complicated, uh, and yeah, involves some very high level math when you talk about probabilities. But to talk about the kind of everyday things that come up in your lives, we don't need such complicated formulas. So, um, today we're gonna talk about two games because I think that probabilities, odds, and expectations are best explained via games, and I like games. So, okay, so I won't here. I'll just note we are jumping around in chapter 16 today. Um, I will try to give an overview of the important concepts using two maybe surprising games. Yes, two games with maybe with results that might be that might surprise you. So two games with results that may surprise you. And in doing this, we'll talk about what should and what shouldn't surprise you about probabilities and what you expect to happen, and then I'll talk about how strange these things can get sometimes. So let's jump right into it. Game one. So here's the setup. You're walking down the boardwalk and you come across a guy playing street games. And you're generally pretty careful about playing gambling games on the street with people because whether or not you have the math behind what they're doing, uh, it's human nature that the odds are probably stacked against you, right? We all walk down and you would think, well, he wouldn't be out here. He wouldn't be out here trying to hustle people if it wasn't a hustle, right? But you hear him out anyway because he's got an interesting spiel, and he tells you that he's a very honest person, and the reason that he claims he's honest is that he will let you pay whatever you decide is fair to play the game. Okay, as long as we're all in agreement that it's a fair price. So let me write that down. On a boardwalk, upward walk, you come across a man who asks you to play you come across a street game. Why not say a street game? You know that normally these games, the odds are stacked against you. Otherwise, how would this person make any money? Sorry. But he claims to be honest. Alright. This reason. You can pay, or the price to play the game is whatever you deem to be a fair price. Okay, and so let's say that you're a good mathematician, and so you say, sure, I'll hear out your game, and then I have these ways of figuring out what a fair price should be. So sure, let me hear out your game, and I'll decide what I think a fair price is. So you decide to hear him out. Okay. And the game is as follows. Okay, so here's the game. I'll put it in blue. The man will flip a coin. I should do this just before somebody texts me. The man will flip a coin until... Well, I say a fair coin, just so that we're all on the same page. This is an honest guy here. The man will flip a fair coin until it comes up heads. So, if the coin comes up heads on the first flip, you win $2. If it comes up tails, the first flip, and heads the second, you win $4. And similarly, it continues like this. So if tails the first 2 times and heads the third, you win 2 to the 3, $8. So this is the game. If the coin comes up tails, 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 heads, and heads on the nth flip, say, then you win 2 to the n dollars. So 2, 4, 8, 16, etc. So do ... If it comes up heads on the nth flip, you win 2 to the n dollars. So that's 2 to the 3, 2 to the, you see what I mean. Good. So this sounds like a reasonable game. And in fact, you should pay some money to play it, because at the least you're going to win $2, right? But that's the question. So how much is a fair price to play? Well, if you want to know how much a fair price is to play, the next question is, well, how much do you expect to win? And if you can figure out how much you expect to win from this game, then that should be a fair price, right? If you say, on average, playing this game, I'll win X amount of money, well, then I think I should pay X amount of money, because if that's an average, then maybe I'll win less, maybe I'll win more, but that seems like a good price to pay. That's the idea behind this expected value thing. So notice that if you get 9 tails in a row and then heads on the 10th flip, you're going to win 2 to the $10. And 2 to the 10 is, notice, if you get tails, 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 heads 9 times. So heads on the 10th flip, you win 2 to the $10. And that's quite a high sum. 2 raised to the 10th. 1024. That's $1,000. Okay, so that's quite a bit. So you expect you will definitely win at least $2. But after that, we need yeah, well, let me just, so you'll definitely win at least $2. But let's calculate how much you would win in general. So being a good mathematician, you recall the expected value formula, which which tends to work well in these kinds of situations. So the expected value formula goes like this. It's going to be quite a mathematical definition, but here we go. So suppose x, capital X, is a random variable, or just a variable, which takes on numerical values x1, x2 through xn. Okay, so in our situation, capital X is going to be a variable which represents how many dollars, and the numerical values it takes on are precisely that, how many dollars. So X is like money. Good. With probabilities, P1, P2 through Pn respectively. So that means you have the probability that you get $x1 is P1. The probability that you get $x2 is P2. The probability that you get $xn is Pn, etc. Good. And with P1 plus P2 plus Pn equal to 1. This is like basically saying that the probabilities all should, when the probabilities all sum to 1, that means that there's 100% chance that one of these things happen, right? Means there is a 100% chance that one of these things happens. That means we have to land on like x1, x2. We have to land on some amount of money. Okay, so suppose x is a variable with takes on numerical values x1 through xn, the probabilities p1 through pn respectively, and the probabilities all add up to 1. Then the definition is we define, so why don't I just say the expected value of x is given by E is equal to the probability of the first thing happens times the first quantity plus the probability that the second thing happens times the second quantity plus the probability that the third thing happens times the third quantity all the way up to the probability that the nth thing happens times the nth quantity. Okay. So that's our formula. And it might look a little bit opaque at the moment, but it's going to be much more relatable once we do some examples. So I'll make a note here that for our purposes, capital X represents dollars. And the little x's represent quantities. Number of dollars we could win. While P1 through Pn are the probabilities that we win that number of dollars. Okay, so let's do some more simple example. So a more simple example, we'll use a classic tool for probability exercises, which is the six-sided dice, six-sided die, singular. So here's a different game. Suppose you roll a fair six-sided die. And that you will win the number of dollars that you roll. What is how much money should you expect to win on average? So this is an important thing. This formula is taking an average is really what we're doing. We're definitely not saying that when you do these calculations and you do get your expected value, that that's exactly the amount of money that you will win. Because the whole nature of these problems is that we're dealing with randomness. And when you're dealing with randomness, the whole idea is that you don't know exactly what's going to happen. So all you can do is take an average. And so what the expected value formula actually represents is like what would you make on average if you were to play this game? If you were to play this game like 1,000,000 times, then what's the average amount of money that you would have made? And you'd think it's somewhere in between, like $1 and $6. It's definitely, you're not going to make more than $6 every roll, and you're not going to make less than $1 every roll. So how do you figure out what the average is? Maybe it's 3, exactly halfway between. But our expected value formula works really well, and so let's give that a go. So note, on average is important because these are random games. So we can't expect to win any specific quantity on a given roll. Just instead, so instead, this tells us what the average amount won per turn if we played many, many times. Okay, so now that I've gotten that written down, let's see. So, you win the amount of money that you roll. So maybe we could make a little table. And so here we'll have the different things you could roll on a dice. 1, 2, 3, 4. 1, 2, 3, 4, 5. And what's the 6th one look like? 1, 2, 3, 1, 2, 3. Matching. Okay. And corresponding to these, we're going to have dollars, right? $1, $2, $3, $4, $5, and $6, because that's how much you would win if you rolled each of these things. Okay. So the expected value, so we have a 1/6 chance of making $1. So why is this? It's because when you roll a die and you have an equal chance of rolling anywhere between 1 and 6, that means you have a 1/6 chance of making $1. These are the kinds of things that I was saying I think are pretty intuitive for a lot of us, but then can get confusing if we're not really specific about what we define a probability to be before we move into more complicated problems. So we have, in fact, because the dice is fair, the die is fair, we have a 1/6 chance of rolling any number between 1 and 6. Good. And so that means that our random variables x1 is $1, x2 is $2, x3 is $3, etc. Up to x6 is $6, because we have 6 different outcomes and 6 different probabilities. P1 is 1/6, P2 is 1/6, P3 is 1/6, P4 is 1/6, P5 is 1/6, and P6 here. I'm gonna P6 is 1/6. Okay. And so now we can just use our expected value formula from up here to calculate this. That's ugly. Okay. So remember, E, expected value, is P1 times x1 plus P2 times x2. Maybe I should use little dots because now I've got x's. P1 times x1 plus P2 times x2 plus all the way up to P6 times x6. And so what that looks like is and what that says in words, I think this is where this becomes much more apparent what's going on, is we have a 1/6 chance of making $1. And then we add to that our 1/6 chance of making $2. And then we have a 1/6 chance of making $3. We have a 1/6 chance of making $4. And we have a 1/6 chance of making $5 and $6 too. Okay. And so we can just add all these up. Either some of the time this will be a difficult formula to simplify. In this sense, it's easy to simplify because we actually have a 1/6 chance of all of them, so we can factor that out. And so here we can actually just divide the sum of all the possible outcomes by 6. It's like finding an average. It's like finding the average between $1, $2, $3, $4, and $5 and $6. So this is 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, I don't know if you all remember, I think I talked about it, this little Gauss trick. This is actually, we can mix these up so that this is 1 plus 6 and 2 plus 5 and 3 plus 4. So that's 7 plus 7 plus 7 is, maybe I'll write that real quick. This is 7, 7, and 7. So what we get is 1/6 times 21. And if you take 21 divided by 6, that's 18, that's 3.5. Okay, so our expected value is $3.50. That's 21 over 6 is 3.5. Okay, so that's our expected value, and that doesn't seem so weird. That we should on average. If we roll the die 100 times, on average, we should win about $3.50 per time. And so this is kind of back to the original question. This is saying that we should think that a fair price to play this game is $3.50 then, because on average, if we play enough times, that's what we should win. Good. This isn't such a weird result. This is like about halfway in between 1 and 6, a little bit higher than 3 because of the weights. Remember, this is really getting back to weighted systems. Remark. This brings us back to weighted systems. I won't belabor that point though. Okay. So, and it works really well in normal cases too. So like if you were going to win $1 no matter what you rolled, you could still use this formula, and it would just it would just give you that you would do 1/6 of $1 plus 1/6 of $1 plus 1/6 of $1 6 times, and you would get an average of $1. So this is basically an average. This formula works like averaging the numbers if each has equal probability of occurring. So maybe I spelled that wrong. Oh well. Okay, but sometimes probabilities aren't even that easy. So here it was really easy to figure out that we had a 1 in 6 chance of rolling any of the numbers on a die, but even if we just have now 2 dice instead of 1 die, the probabilities get a little more tricky already, and so I'll just do one of those examples briefly. So, sometimes calculating the probabilities is not this simple. So let's change the game. If instead you roll 2 dice and win the amount that you roll, what about how much money should you expect to make? Okay. Well, so here let's do a table to figure out the probabilities, because the thing to notice is that notice there's only one way to make $2, and that's if you roll 2 ones. But there are 2 ways to make $3. You could either roll a 1 on the one dice and a 2 on the other, or you could roll a 2 on the first die and a 1 on the other. There is only one way to make $2, i.e. roll snake eyes. But 2 ways to make $3. And that's, say you had like a red die and a black die. So either you have a 2 on the black die and a 1 on the red die, or you have a 2 on the red die and a 1 on the black die. So that's 2 different ways. And so the way that we're going to sort this out is we're going to put it all in a table. So the first question. Okay, so the first question is how many possible results can we get from rolling 2 die? So this goes back to some of the combinatorics. You remember when I had a day where I just talked about how to count things, and this is one of those things. And it gets back to that tree diagram that I was drawing on the board. So recall our class on combinatorics. How to count. And so one of the things one of the techniques that we used was one technique was the multiplication rule. And basically the multiplication rule says that if there are m different ways to do x and n ways to do y, then there are m times n ways to do x, then y. So basically, if you want to know, this gets back to questions like, say you want to send postcards to 2 different friends, and there are 5 different postcards to choose from. Well, you have 5 different options to send the first friend, and 5 different options for what you send the first friend, and then for each of those options, you have 5 different options for what you send the second friend. And so that makes 5 times 5 total different ways of doing it. So recall our tree diagram. So this is basically saying that, like, if you have m options for the first thing, and then depending on what you do with the first one, then maybe you have n different options for the second one. So this is like, you choose to send 1 postcard to your first friend, and then you choose to send this postcard to your second friend. So this is n options. And the outcomes, the overall outcomes, are these like little end bits on the tree, what we call leaves on the tree. That's actually a technical term, the leaves. And the total number of leaves that we get is the number of options. So number of leaves is number of options is m times n. So basically all I'm really saying is that here, if we have 6 options for the red die and 6 for the black die, we have 6 times 6, which is 36 total possibilities. And so this is really obvious in this kind of case, because we can also make tables. We don't need this tree necessarily. We could make a table. So let's try a table. Here is a table of possible outcomes. Okay, so our table is going to look like this. So I'm going to have like it's going to be about a 6 by 6. And here. One, two, three, four, 5. I needed to make it a little longer. Why don't I? Good. That looks nice, actually. Good. Okay, and so up on top, I'm going to draw our options for our black die. So this is supposed to be a square, if I can draw a square. Oh my god, it really doesn't think I can draw a square. Oh well, that's our black die, and I'm going to copy and paste it because that was really a pain. Okay. So there's our black die, there's our black die, there's our black die, there's our black die. There's our black die, and on this black die we're going to have different options. So either it's going to have a... So this is the option for 1, this is the option for 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. Okay. And then I'm going to do that, and I'm going to say, actually, color. This is going to be our red die. And now I'm going to copy that one. Paste. Oops. So color it red. Oops. Color it red. And then copy it. Paste. 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 So here's our little table. And let's write in our table here. So first of all, it should be quite obvious now that we have 36 options, because this is a 6 by 6 grid, and that's like how we make. That's how we learn to multiply to begin with. Really, this is like the foundations of why we multiply to begin with. Very important. Okay, and so in the boxes, we're going to put the outcomes. So this outcome means you make $2. This one means you make $3, right? $1 on the red die, $2 on the black die. This one's $4, $3 on the black die, 1 on the red, 5 for 4 and 1, 6 for 5 and 1, and 7 for 6 and 1. Okay, and now I'm going to drop the dollar signs, but we do the same kinds of things. So 2 and 1 makes 3, 2 and 2 makes 4, 2 and 3 makes 5, 6, 7, 8. I think you guys probably see the pattern now. So 3 and 1 makes 4, 3 and 2 makes 5, 3 and 3 makes 6, 7, 8, 9, 5, 6, 7, 8, 9, 10. 6 and 1. Oh, I forgot. I did a wrong thing. This one should go here. And this one should be 5. Okay. So now on the 5, 1, 5 and 1 makes 6, 7, 8, 9, 10, and 11 for 6 and a 5. And finally we get a 7, 8, 9, 10, 11, 12. And so the thing to notice here is that, yeah, we have 36 different outcomes, but they're not all different. So, like, this one is the only place we see a 2. However, we see 3s on both of these options, right? And then we see 4s. I have 3 different ways of making $4. And we have 4 different ways of making $5. And then we have 5 different ways of making $6, 6 different ways of making $7, 5 ways of 8, 4 ways of 9, 3 ways of 10, 2 ways of $11, and finally we only have 1 way of making $12. That's rolling 2 6s. Okay, so now we can calculate our expected value, right? So what's the probability? So we have our outcomes. X1 equals $2. X2 is going to be $3. X3 is going to be $4. And so how many outcomes are there in total? 11 of them, right? Because X11 is going to be $12. And what are their probabilities? Well, the probability that we get $2 is 1 out of 36, right? So P1 is just 1 out of 36. Now the probability that we make $3, though, is 2 out of 36. So P2 is 2 out of 36. P3 is going to be 1, 2, 3 out of 36. Etc. Until we get up to the probability that we make $7, which is P6, is going to be 6 out of 36, right? We said there were 6 different options for 7. 1, 2, 3, 4, 5, 6. But then it's going to go back down again, so then P7 is going to be just 5 over 32. That's how many options we have for 8. 5 over 36. E8 is 4 over 36, etc. And then it starts going down again. Don't worry if the P's and the X's are confusing you a little bit, because now we'll go and do it with just the numbers, and it makes a lot more sense to me. So the expected value E is, well, we have a 1 over 32 chance of making $2 plus a 2 over 36 chance of making $3 plus 3 over 36 chance of making $4 plus 4 over 36 chance of making $5 plus 5 over 36 making $6 plus a 6 over 36 chance of making $7, and then we start going down again plus a 5/36 chance of making $8 plus 4/36 times $9. Oh boy, plus 3/36 times $10 plus 2/36 times $11 and plus 1/36 times $12. Okay, so that's a lot of things. You could either enter it into a calculator or you could do it like this. If you notice, we can kind of pull a 36 out. I don't know why I wrote 32 there. I meant 36. We can pull a 36 out, and this is 1/36 times 2 plus 2 times 3 plus 3 times 4 plus 4 times 5 plus 1 times 12. Anyway, what I've done is just I've already done this out for you, so I won't necessarily do it again. But so where did I do it? What this gives us is $7. You can put it into your calculator. So your expected value is $7. That seems pretty average. So this works how you think it will. Okay. So now we want to go back to the coin flip game. To our street game. So, you think to use this formula. Okay, and so you think, okay, so you have an expected value of, well, let's do the probabilities first. The probability you get heads first time, first flip, is 1/2. And the probability that you flip, you get tails, then heads, well, we'll use our multiplication rule, is 1/2 times 1/2, which is 1/4, right? So you have a 1/4 chance of getting tails then heads. So similarly, the probability you flip tails, then heads is 1/2 times 1/2 times 1/2, which is 1/2 cubed, which is 1/8. And the probability you flip heads on the nth try is 1/2 to the n. And remember that our variables were exactly 2 to the n dollars. This is when the paradox arises. So, the expected value equation gives us that E is going to be the 1/2, the probability that you flip a heads first try, times the amount of money you win if that happens. So that's times $2. And then we're going to add to that the probability that you get a heads the second flip, which is 1/4, times the amount of money you win in that case, which is $4. And then we're going to add to that 1/8, which is the probability that it happens on the third flip, times $8, which is your reward if that happens, plus 1/16 times $16, plus 1/32 times 2 to the 5th, which is $32 forever. All right. That's a bit weird that it goes on forever, but maybe that's what I'm hinting at. Because if we simplify this, well, 1/2 of $2 is $1, and 1/4 of $4 is $1, and 1/8 of $8 is $1, and 1/16 of $16 is $1, and forever. And so you see that the probability is exactly 1 over the amount of dollars that you would win in that case every time. And if this goes on forever, this adds up to infinity. This should be dismaying, right? Because, of course, you shouldn't give him... It seems absurd to give him any more than, like, even $50, right? When you've got 50% chance of only making $2 off of the whole ordeal, and a 75% chance of making $4 or less, then it would seem absurd to give him very much money. But in fact, this expected value formula gives us infinity. Should we trust it? I mean, have we done something wrong? Are we supposed to be using the expected value? Like, it seems like a very logical way to solve this problem. And we remember how the probabilities were all supposed to add up to 1. And now you might be thinking, well, now we've got infinitely many different options. Well, that's a trick. We've got infinitely many different options. But funny enough, these probabilities all do still sum up to 1. Do the probabilities... And if you watched my lecture on geometric series, you would have seen this. Really sum to 1? Well, let's look at it. The sum of the probabilities is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 forever, right? And so if you remember the trick, I said, all right, well, what's 1/2 of that? Well, if you do 1/2 of that, then you're going to distribute the 1/2 through. So that's 1/2 times 1/2, plus 1/2 times 1/4, plus 1/2 times 1/8, and so on. And so what we'll get is 1/4, 1/2 times 1/2, plus 1/8, 1/2 times 1/4, plus 1/16, 1/2 times 1/8, plus 1/32, 1/2 times 1/16. Forever. We'll subtract these off, and when we subtract them off, we're going to do 1/4, so 1/2 minus 0 is just going to give us a 1/2 here, and then everything else is going to cancel. 1/4 minus 1/4 is 0, 1/8 minus 1/8 is 0, 1/16 minus 1/16 is 0, so everything forever, infinitely far, cancels. And what we're left with is just 1/2 of p, right? P, 1 of p, minus 1/2 of p, leaves you with 1/2 of p. So we can multiply 2 on both sides, and we get p is equal to 1. So indeed, all of our probabilities do add up to 1, and that's not where the problem is coming from. The problem is actually coming from the fact that we have this divergent series here. But, good. So what? I mean, so you should... So what would a fair price be? For the boardwalk? For the street? For the coin flip game? In fact, the expected value is infinite. So no price, no matter how high, is fair. Thus, you don't play. But this really is paradoxical, in the sense that, like, what does it mean to have an infinite expected value? Certainly you wouldn't expect to make any more than like $10 off of the game. But you know, deep down, that if you could get a heads on the 10th flip, which seems pretty possible, you would win more than $1,000. The problem is that your probability of getting heads on the 10th flip is actually much lower than you might think it is. You have a 1 in 1,000 chance of getting a heads on the 10th flip. So that's why you'd make so much money if that happened. Good. So that's that. That's my funny expected value paradox. And now I just have one more funny paradox having to do with probabilities. So now, one more game, or more appropriately, paradox, involving probabilities. This one is called Monty Hall. I'm sure many of you have already heard of this game, or at least of this man. He was a Canadian game show host of Let's Make a Deal. And this problem is this is a mathematical problem inspired by Let's Make a Deal. Well, I guess it's related to Let's Make a Deal. It really wasn't Monty Hall who came up with this idea. This is kind of an ancient problem, maybe not super ancient, but dating back at least into the 18th century with Bertrand Russell. What century did he live in? Not 18th. But has deeper roots in Bertrand's box paradox. This is another one closely related. Bertrand Russell had a lot of interesting paradoxes. He was a logician, and I think I've maybe told you about one of his paradoxes before, which is that in logic you argue that one can base any statement, one can prove any statement if you start with a false premise. And Bertrand Russell even claimed that then no matter what the false premise you start with is, you can take that to proving anything you would like. And the story goes that one of his students raised their hand and said, "Oh yeah, well, prove to me that if 1 is equal to 0, then you are the Pope." And Bertrand Russell thinks about this for a minute, and he responds, "Well, if 1 is equal to 0, then 2 is equal to 1. You just add 1 to both sides. So then a set with 2 things in it is the same as a set with 1 thing in it. The set containing myself and the Pope is a set with 2 objects. But if 2 is equal to 1, then the set containing me and the Pope is the same cardinality as the set which contains just me and the set which contains just the Pope, and therefore I am the Pope." So that's a little bit of Bertrand Russell logic for you, but this paradox is a little different. So here's the game. Suppose the game. Show. Why don't I? Here. Cut, and I'm going to start it here. Suppose you are on a game show and are presented with 3 doors. Behind one of the doors is a new car. A mu car. A new car. Behind the other two are goats. You don't know which is which. Okay. So the idea is this. You pick a door. So you pick a door. The host, who knows where the new car is, where the goats are, opens one of the doors, behind which is a goat. He then asks you, he then asks, would you like to stick with the door that you've chosen, or would you like to switch doors? Okay, and so the question is really, does it matter? So the question is there a strategy? Does it matter if you switch? So I'll let you ponder that question for a second while I draw some doors. That sounds like a fun thing to do. Let's do brown like that for a door. Looks like a pretty good door. Okay, I wonder if it'll let me do like a nice... No, it doesn't like that kind of shape. Oh well. I'll just make these doors like this. So there's one door, and there's two door, and there's three door. Pardon my artistic abilities. And the doors, let's label them A. Here, I'll use a thinner one. A, B, and C. So remember, you pick, let's say you pick A, without knowing, of course, what's behind it. And Monty, or the host, opens door C with a goat behind it. Okay, so here's my little goat. I don't know. It's not really a goat, but it's definitely not a car. So at least we won't get confused. So now we know that there's a goat, so you chose A. And we know that there's a goat behind C. And then he asks you, do you want to switch? And you're kind of look at him a little confused because you think, well, of course I don't want to switch. There are two doors here. I don't know what's behind either of them. So I have a 50-50 chance, right? So it doesn't matter if I switch or not. One argument is that it doesn't matter. if you switch. There are 2 doors left. You don't know which one has the car, so it's a 50-50 shot, right? Well, I claim that you're wrong. I mean that I'm wrong, but let's see why. I mean, I think it's really, there are a lot of people, even when this was published. So this is a question that got published in a magazine actually in the 90s, and by I can't remember what magazine in particular, but one of these science math academic magazines. Had tons of people writing in saying, no, 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 you're wrong, you're wrong, you're wrong. It doesn't matter. It's a 50-50 chance. And yeah, even some really famous mathematicians didn't believe this result when it came out. But the logic is just insanely simple. So the answer it is better to switch. Strange. Why is that? Well, let's actually look at let's look at it in a slightly different way. Now, instead of just looking at what happens at the end after he opens the door and you think, okay, well, do I take the car or not? Let's think about it from the very beginning. So, from the beginning, you had a 1/3 chance of picking the door. Or the car, right? Good. And then the real trick behind this is that if you picked the car, and if you had that 1/3 chance and you actually did pick the car, then it doesn't matter which of the doors the game show host opens. Both of them have goats behind them, so he opens either one of them, and if you switch, you lose. You win a goat instead of winning the car. But in the other 2 out of 3 scenarios, say you pick the door that has a goat behind it first, right? So say you pick A, B, C, doors. So say you pick A, and there's a goat behind A. Goat. Well, then say maybe let's say that the car is behind B. Car. Why don't I make it a shiny red race car? That would be fun. Car. And another goat. He doesn't get to be shiny and red because he's just a goat. Okay, so you pick A. And now the host can only open either door B or door C. The host has to open one with a goat behind it, so he has the choice of opening B or C, but B has the car, so he's going to open door C. Then the host must open C because B has a car. So in this scenario, so now the host opens C, and now if you stay, you lose, and if you switch, you win. So in this case, switching wins. And so that's really the whole explanation there. I'll write it out if in a table form, but that's really it. So we can summarize this in a table. and it goes like this. We have you pick either door A, B, or C. You switch, or you stay. These are really this is the whole thing. And because, like I just noticed, depending on what door you pick, you definitely know you're either going to win or you're going to lose if you switch or if you stay. And so let's say you pick A, and he opens C, and you switch. So then you get B, and you win. Sable. So if the car is behind door B, we can summarize this in a table. So you pick A, and you switch, and you win. So let me do win in like green. So win, dark green. And if you stay on door A, then you lose. Okay. So now if you pick B, then you've picked the car right off the bat. And so he opens either door A or door C. Let's say he still opens C. So you've picked B, and now you're still left with just A and B. So if you stick with B, then you're going to win. And if you switch to A, you're going to lose. So switch, you lose. Stay, you win. And if you had to pick C, then he would have to open door A, and then you would win if you switched to B and lose if you stuck with C. So win and lose. And so what we actually notice here is that in 2 of the 3 scenarios, you win if you switch, and in 1 of the 3 scenarios, you lose if you switch. So this means that you win 2/3 of the time if you choose to switch. Crazy things. I'll let you ponder that. But yeah, so those are my 2 fun games for today. Hope you enjoyed them like I do. Yes.